connectives, quantifiers, these things. We started to talk about them. So today I'm going to talk about connectives and propositional calculus. So calculus is just the thing that you use to compute with. So sometimes this is called Boolean Algebra, too. So that's what we're going to talk about. So given propositions, okay, we can form new propositions from old propositions. New propositions. Okay, so let me show you some of them that we can form. So we can form this thing. So this is conjunction or and. So this is P and Q. Okay. Another one you can do is a disjunction P or Q. P or Q. So this is a new proposition, and it'll have truth values which depend on the truth values of P and Q. And another one you can do is not P. Okay, so this is not P. Okay, another notation for this. Another notation that is used commonly in like programming languages. So is not P. So this is another notation. So this is an exclamation point for not P. Okay? And so I want to talk about how these things will behave. Okay? And so I need to tell you how P and Q, what the truth values of these things are, given the truth values of P and the truth values of Q. And to do this, we use what is called a truth table. Okay, let me move this out of the way real quick. Okay, so so we're going to talk about logical and. Okay, and so for this one, I'm going to form what's called a truth table. Okay, so I take P and Q here, and I'm going to take the truth. So what I'm going to put is the possible truth values for P and Q. Right? They could both be true. This could be true. This could be false. This one here could be false, and this one could be true, or they could both be false. Okay? And for this proposition to be true, what's going to happen is that both of these things are necessarily going to need to be true. So this will be true. This will be true. Or sorry, this one will be false because one of them is false. So both of them are not true. This is false. And this is false. Okay, so the only time P and Q is true is when both P and Q are true, right? So it does like you expect it to. Logical or is a little bit different, right? So again, I'm going to make a truth table to explain what I mean here. Okay, and what's going to happen is that this thing's true only in the case when one of them is true, and this differs from English. So here, both of them are true, so this is true, right? This thing's going to be true. This is true, and the only time it's false is when both of them are false. Okay, so it's kind of the opposite of this thing. Okay, so. All right, so this is the truth table for P or Q. I want to give you an example and a warning. Okay, so that first, let me give you an example, right? So let's do an example. So let's consider, and then where can you guys see? Can you tell me where, like here? A bit lower? Like here? There? Zach? Is this okay? Okay. So, so let's do this one here. So let's give you an example, okay? So let's consider the proposition 1 is equal to 0, or 2 plus 2 is equal to 4. Okay? So we have two things here, and I'm doing logical OR. So this thing here is true, right? This thing here is true because this one's true, right? This one's clearly false, right? But I only need one of them to be true for this thing to work, okay? And so let me give you a warning that this is different. This is different from the usage in English or other natural languages, right? So, so I've got a dog named Buddy, right? And if my wife asks me, so we had to leave, and she's like, do you want to crate Buddy, or do you want to take Buddy with you? And I was like, yes. But you don't really say that, right? No. I was actually just not paying attention. But if we did use logical OR like we would in, use logical OR like the OR in English, that would have been a perfectly normal interaction, right? But we don't. That's not usually what we mean when we say OR in English, right? Okay. So, all right. So, yeah. Okay. So let me just, one more thing is negation, okay? So the last thing is negation. So this is not, right? And so here we have P, and then we have not P. Okay? And when this is true and this is false, it just flips the value here. Okay? So it just flips everything. All right. Okay, so let's make another example. Okay, so I'm going to compute some truth tables using this stuff that we've already done. So what we could do is we can try now make more complicated propositions, right? So if I've given propositional variables, or these like P, Q, R things, right? I can take combinations of all these operations to make a new proposition. Okay, so let's do an example here. Okay, so here, let's compute the truth table for the proposition for P and not P. Okay? So here, P can only take on two values, right? P, and then this is P and not P. Okay, so this is true and this is false. Okay, so not P flips this. So this will be true and false. And, okay, so when you do true and false, this is false. Okay, because they both need to be true. Or you could do false and true, right? And this is false as well, right? So this thing here is always false, right? So the proposition P and not P is always false, right? And so when you have a proposition, so okay, the most basic proposition you could do would just be true or just be false, okay? So if I were just to say true, return true, that would be a proposition in itself. And this, since this proposition here has exactly the same truth value as f, we say it's logically equivalent to false, right? And sometimes we just write it like that. So we could say P and not P is equal to f, because they're exactly the same thing. Okay? So another example. Right? We could do something similar. We could do P or not P. Okay? So here, what do we have? So here, let's do this one. I'm going to compute the truth table for this, or not P. Okay? So this could be true or this could be false. So there's one input, so we have two things. So this is true or false. Okay? And that's true. Okay? And this is false or true. And that's also true. So this statement here, P and not P, or not P, is always true. It's logically equivalent to that simple proposition, which is just true. You know, like if you're just going to make a sentence that was just true, you know, this thing's the same thing. So this is logically equivalent to true, is equal to true. And these things are called tautologies, right? Things that are always true. This is what's called a tautology. Okay. So that's what I wanted to do. Okay. So now, so if you guys go to handout 1, now we're going to do some exercises, and I'm going to go around and help you guys with some exercises. Okay. So let's talk about this the problem real quick. So every student in this class is a math major and a human being. So we need them both to be a math major and a human being for this to be true, like both of them, right? Not everyone in here is a math major. Okay, so we're going to assume not everyone in here is, who's not a math major, right? Okay, not everyone in here is a math major, okay? I should have said that from the beginning, and that's why we were asked that. So this is false. This is a false statement, okay? The proposition is false. So every student in this class is a math major or a human being, right? Well, everyone in here is a human being, so the statement's automatically true, okay? Because they don't need to be, you know, it's not an or thing. Okay? You guys get it? Okay. Cool. All right. So now what I want to do is so we have kind of the basic setup here. And what I want to do is I want to explain how to manipulate propositions using some basic rules. Okay? And so this is sometimes called Boolean Algebra. So I'm going to do a little heading here, and so P's and Q's. Oh yeah, there we go. So P's and Q's. P's, Q's, R's. So these things are called propositional variables. So they're holding the place of a proposition. Variables. Or what are called Boolean sometimes. So these are things that'll be true or false. We don't really care what the propositions say. Like that's kind of the semantics of things. We just care that it's something that returns true or false. Okay? So, okay, and Boolean algebra is how to manipulate these things using and, or, not, all that stuff. Okay? So here's an example of a rule that I want to show you guys. Okay? So here's a claim. Okay? The claim is that not P and Q, okay? This is logically equivalent to not P or not Q. Okay? For this thing to be false, one of these two things has to be true. You can kind of already see it, right, if you just think about it, right, given the rules. But to do this formally, we're going to check this with a truth table, okay? So that these things are logically equivalent. They're going to have the same truth table. So, so proof. Okay? So to verify this, so we use, and then I'm going to go all the way over to this board up over here. So to verify this, we're going to use a truth table. So we use truth tables. Okay? And so we're going to show that those two propositions, the proposition on the left-hand side and the proposition on the right-hand side here, that they're going to have the exact same inputs and outputs. Okay? So let's do it. Okay? So we're going to do P. We're going to have Q. Okay? And then I need to do, well, let's do not P and Q. Okay, and so maybe we could do, okay, so this is going to be one side of it, right? And then the other side, we're going to compute, so I'm just going to do these first, but then we're going to do not P or not Q, okay? So over here, I'm going to compute the second side, okay? And so what we need to show is we need to show the thing in this column and the thing in this column are exactly the same, okay? Since we have two inputs here, right, we need to check all the truth values here. And so what are the possible truth values? True, 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 false, false, true, false, false. Okay? And, okay, so now we know what and is. Remember and was like, both of them have to be true for the whole thing to be true. And so we're going to not that. So this is not true. So this is false. This is not false. This is true. This is not false again, which is true. And this is not false again, which is true. Okay? So this is false, true, 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 according to these inputs. Okay? And so I just did this thing here, this output there. That's the output of the and thing that we already did. Okay. So now let's just flip this, and we'll flip this. That's what this thing is going to do. So let's flip them. Okay? So this is false, false, true, true. Okay? And then we flip this one too. So this is false, true, false, true, false, true. Okay? And all right, so now what we're going to do is we're going to do the logical OR to these things here. Okay? And logical OR is true only when both of them when one of them is true, right? So what do we get here? So this is false, OR of that. One of them is true, so it's true. One of them is true, so it's true. And one of them is true, so it's true. Okay? And the two columns that we wanted to compare were this column and this column, corresponding to this side and this side of the equality. Okay? So what do we have? So here we see false, true, 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 false, true, true, true. Okay? So because the truth tables, yeah. Did someone want to say something?
Well, did you say that the last column, it would only be true if only one of them is true? Or
Yeah, for one of the, yeah, when only one of them is true, because this is an OR,
yeah.
right?
So would the last one at the bottom not be?
No. You only need one, right? It's only one. So if you did it that way, that would be called an exclusive OR, right? So yeah, and that's sometimes what we mean, I think, in English, right? We usually mean this exclusive OR thing. But that's not what we mean. If both of them are true, it's cool, right? Yeah. Okay. Since because the truth tables for this proposition not P and Q and not P, so we have not P or not Q are the same, comma, the propositions, and then I'll continue up on this side of the board, the propositions, so the propositions are logically equivalent. Does it smell like it's burning? Wasn't there a fire in here? Or somewhere recently? It was next door, yeah. It totally smells like it's burning, right? Okay, well, we might have to leave soon. It's kind of weird, right? Okay. Anyway. Okay. Burning rubber or something? Yeah. Okay. Maybe someone's just like, someone's grinding out their drill. I don't know. Okay, motor burning. Okay, cool. Anyway, so these are logically equivalent. Okay, so when I start a proof and end a proof, right, I'm going to just kind of make a little thing here. Some people like to put boxes, or like some people write QED, whatever. Okay, I do this little thing. It's like 2 dashes. Okay, so that's what we have to say about. That's all I have to say about this one. So here, now we kind of have a rule for manipulating. So if we have an and, we get to distribute this not and flip the or. Okay, and that's kind of the algebra part of all this. All right, and where did I put the notes here? Okay. So, okay. So let me also make like a little remark here. So not P and Q. Sometimes this is called NAND. So if you're an electrical engineer, right, all the circuits, all these like logical things that you do, they build them all using a NAND thing. So you can actually kind of like program logical propositions into wires. Okay, and they do them all with this NAND thing. Anyway, okay, so this is similar. So there's a similar rule. So there's a similar rule for disjunction. And together, they form what is called, they form De Morgan's laws. So this stuff's really old. I don't know laws. And let me write down what De Morgan's laws are. Okay, so De Morgan's laws. Okay, so here there's two of them, right? It says not P and Q is not P or not Q. Okay, and so this is these parentheses here. If I didn't have this parentheses and you mistakenly thought that this was like not this whole thing, right, then you'd get something different because of the distributive rule. So kind of parentheses are kind of important here. Okay, the other rule is not P or Q. Okay, so for P or Q not to work, right, what do you need to happen? Well, you need not P. So this thing's false, right, exactly when you don't have P and you don't have Q. Okay, not P and not Q. So these two things here, these two things are the De Morgan's laws. Okay, and it shows you how to distribute nots into ors and ands. Okay, so hopefully I'm not yelling. Okay, so there's other rules. Okay, so there's other rules that we can use too. Okay, there's distributive rules, and distributive rules involve three propositions. Okay, so there are also distributive rules. Okay, let me make a remark here. So I proved this one here, right? I'm going to have you. What did I prove the or? I proved the and one here, right? I'm going to have you guys prove the or one in the homework. Okay, so that's going to be on Friday. That's going to be due Friday. Okay. So there's also distributive rules. So let me do the distributive rules. So the distributive rules show how and or distribute other each other when we have three propositional variables. So here are the distributive rules. Okay, distributive rules. Okay, and here we go. So P and Q or R. So this is the same as P and Q or P and R. Okay, so this is distributed. So this is how and distributes over or. So you can have P or let's say P or Q and R. So this is equal to P or Q and P or R. Okay, so this is what we have here. Okay, and so to prove these, we prove these via a similar truth table method. So we show these these logical equivalences using truth tables. Okay, so let's take one of them. So what I'm going to do here is I'm going to do one of the truth tables, right? And then I'm going to have, so here's what I'm going to do. I'm going to take, I don't know, let's see, which one did I write down here? Doesn't really matter. So I did the or one here. So I did this one here, okay? And so all I'm going to do this side, okay? And then in class, after I finish that, I'm going to have you guys do this side. And then for homework, I'm going to have you do this full one here, okay? So I'm going to start, right? I will start. Oh, let's see, that's too low. That's too low. Okay. Okay, so let me show you how this goes. Okay, how does these things go? It's very similar to this, right? We're going to build a big truth table, and then we're going to build a big truth table and we're going to show that they're the same. Okay, so we need to build a truth table for the left-hand side and a truth table for the right-hand side, and we need to show that they're the same. So let's look at this one here. Okay. So to prove these identities, we use truth tables and show of both sides. And show they are the same. Okay, so from star, so the left-hand side, so here, this is what I mean by left-hand side of star. Okay, so this is what I'm going to do. I'm going to start doing the truth table for this thing. So we're going to have P. So now this thing's going to get a lot bigger, okay? Because look, how many inputs do we have, right? We have 3 inputs. When we had 1 input, we had 2 possibilities, true or false. When we had 2 inputs, we had 4 possibilities. And when we have 3 inputs, we have 8 possibilities now. So now we need to check the output of that thing for all 8 possibilities. Okay? So we're going to have P, Q, R, like this. Okay? And so to make things easier, like I did before, I'm going to do an auxiliary thing. Okay? So I'm going to do Q and R. And then here I'm going to do P and Q and R. Okay, so I'm not going to be able to fit 8 here, so I'm going to have to continue this on to the next board, unfortunately. Okay, so I'll just do this again here. Okay, so here is the first part of it. So we'll do P, Q, R. And then we did Q and R. And then we did, oh, sorry, P or Q and R, right? That's what we want here. Okay? P or Q and R. Okay? That's the proposition that we want. Okay? So here, we could do true, true, true. Okay? True, I'll just keep these ones to be true here. True, false, false, true, false, false. Okay? So that's those are the possibilities here. The other possibilities will be something similar, but this is going to be false, false, false. And then we have the exact same thing over here. True, 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 false, false, true, false, false. Okay, so let's work on this column here. Okay, this column only involves Q and R, so we're only going to be concerned with this. So for Q and R to be true, right, we need Q to be true and R to be true. And the only time that happens is in the first one. So these are false, false, false. Okay, here, again, it doesn't involve the P's. So we're going to have the exact same thing over here. True, false, false, false. So we're just using these 2 parts here. And this thing repeats over there, so it's going to be the exact same thing. Now we're going to do OR, and we're going to do OR between this one and this one. Okay? So that's what we're going to do. An OR is true when only one of them is true. So this is true. This is true. Well, you can see all of these things are true, so they're all going to be true here. True, true. Okay? And now on this side here, well, these are all false. Okay? So the only thing that really matters is the truth value over here. So this is true, false, false, false. Okay? And now we've built the complete truth table with the 8 outputs for P or the quantity Q and R. When I say the quantity, it means that I'm looking at this expression in parentheses. All right. So that's what we have. So any questions on how I computed this truth table? Yeah.
Just a question on convention. Is that the typical way that you would write out true, like the order of P, Q, and R as far as trues and false, the combination?
I don't know. So some people, maybe this is one way of doing it. There's other ways of doing it. I think what maybe, if you consider true and false as like 0 and 1, right? Well, then this would be starting like 1, 1. And that's not really counting up in binary. The counting up in binary would be like false, false, and then you do 0, 1. So it'd be 0, true. Yeah. So you could do it that way, or you can do it this way. Okay? So they're both okay, right? Or you can do it your own crazy way, right? So it doesn't matter. You can. It has no. The order has absolutely no bearing onto the truth of the truth table. It just makes it easier or harder on the reader, right? And yourself, right? Because here, like for example, if I wrote these in a random order, right, I couldn't have just like copy pasted this part over to that part. You see? Like so the fact that I wrote it in this order makes it so that I can read this part exactly the same as this part, right? You guys catch my drift? Okay. But logically it doesn't matter at all. Yeah. Okay. So to finish the proof, finish proving logical equivalence with the other side of this, which is not P or not Q. Oh, no, sorry, that's not what we're doing right now. I was looking at that table for some reason. We're doing this one here. P or Q and P or R, we need to compute the truth table. Compute this truth table. And compare it to the first. Okay, so all right, so that's what we have. Okay, so that's the distributive rule, and so this is going to be done at the end, right? So let's see how much time we have here. When do we end? 40. Okay, good. Okay, so we leave this at the end. Okay, so we'll do this at the we're going to do this. We will do this exercise. And in class exercise. So I'm going to come around and have you guys check this. Okay, and then the other one's going to be homework. All right, the other things. There's two other things that there's other things that I didn't say. Okay, so other rules. And these rules are kind of the silly rules. Okay? The other rules are the following, right? Not P is P. If you do not twice, if you flip twice, you get back to the original thing. What's another stupid rule that I could write down? P, well, yeah, I could say, well, here I have this one. P and Q is the same thing as Q and P. Right? That's a pretty stupid one. Here's another stupid one. P or Q is the same thing as Q or P. Okay? So the logical order doesn't matter. You can check that truth table if you want. Technically, like in logic, we should technically try to, do all the details, right? And so these are things that I have to say. What's another stupid rule that I could say? So this is the commutative property.
Is there associativity?
Yeah, associativity. Okay, so we have associativity. So P and Q and R. So if I were going to do this, so this is the same thing as P and Q and R. So it doesn't matter which operations I do it in, right? So P or Q or R. This is the same thing as P or Q or R. Okay? And so this, the reason why we write this, so this is associativity. Okay, and the reason we write these ones down is because it allows us to, you can just do quick manipulations. But you can check this one. These ones are not hard to check. But it also allows us to just get, when there's three things here, it allows us to get rid of parentheses. Okay, so in the notation, right, it doesn't matter. So technically, right, we define these operations to be between two propositional variables, not three. But it turns out it doesn't matter which order you do it in. So the operation of and between three things is what's called well-defined. It doesn't matter which order we do it in. Okay? So, okay. So now what I want you to do in class is I want you to do the following. So on handout 1, so for handout 1, which is on the web page, okay, the course web page, I want you to do the following. So do 3.1, 3.2, and 3.3. Okay, so these are negations. These are things, I just want you to negate some, it's really simple. And these are actual propositions, and I want you to think about what it actually means to negate them. You don't really have to, you shouldn't have to think too hard about these. So don't try and use the symbols too much. Just say what the opposite of what the statement is. Okay, so I want you to do 4.3. So this is the other De Morgan. I think this is also on the homework. I want you to do you guys understand what I mean by 3.1, 3.2, 3.3? There's like one heading and then there's the other one. Okay. Then there's 5.1. This is the finishing of the distributive property. So finish the distributive property in class. Okay, and then finally, there's 6.1 and 6.2, okay? And these are the most interesting, probably. And so this is how to prove a logical equivalence without using truth tables. So after we have all those rules, the distributive rule, the De Morgan's rule, we can use those to prove propositions are equivalent without resorting to truth tables. So prove propositions are equivalent without truth tables. Okay? So that's what I'm going to have you guys do.